McMahon is a PhD Fermilab Fellow from a while ago. And he's now at the University of Michigan. He's an associate professor there, works on the CFD experiment, doing a lot of very cool things, and I imagine we'll talk about some of that today. I was looking through his, to figure what to say, and I noticed he was an undergraduate at Berkeley. I'm so bad. But he worked with Charles Towns on doing a interferometer, so I think we're talking about timing, interferometer at a couple micron wavelengths, but using coherent detectors, not re-imaging. Right? So that's, I don't know what he did on that. That's a very interesting project. Those in radiation vision are also very hard to get low noise in. We get at those wavelengths, but that's another time. He went on from there to Princeton and worked with Suzanne Staggs, who was also an EFI fellow here. Worked on CMB polarization before it had been detected. In fact, back when they used to do experiments in New Jersey, and worked in the HatMap project in New Jersey. From there he came here as a case fellow. He worked on FPT. And there are so many stories of Jeff working on ACTPol, on FPT, while he was at ACTPol. I started writing down, and I couldn't find any that we could say in this, audience. Although there is one, is that when you go down to this ACTPol, it's at altitude, right? And you can't, you're on the mountaintop, so to speak, but you just fly there and you get off into the mountaintop. So they're always trying to convince you to take all sorts of things to help you with climate change. One of them, when we were going down, was dynamos. How many have ever taken dynamos? South Pole people. Yeah. Anyway, it turns out there's a peculiar possible side effect from dynamos. Very, very rare. But I was already at the pole and waiting for these guys to get in. And the plane arrives, and so Jeff, for the first time, he gets him off this plane, and you're going to see the South Pole. And he gets off, everyone's getting off, it's windy, it's cold, and it's vulnerable. And Jeff gets off, and he doesn't have a hat on, doesn't have goggles, his jacket's wide open. And he's saying, I'm blind! I'm blind! It turns out that in a certain fraction of the population, dynamos makes you temporarily blind. Very, 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 very nearsighted. Maybe that's the story I should tell.
There may be others.
Building the telescope in Texas and climbing towers, and the telescope's moving quickly, and I can't tell those. But Jeff has done a lot of terrific things, both for SPT, and then after that he started at Michigan. There he started a whole program with a very good group and worked on detectors, this collaboration between NIST, Chicago, and Princeton, which produced detectors that are in the field, a whole field of meta material, anti-question codes, not great place and things. I'm sure we'll hear about that. He's been working, for a while, he was working both in South Pole and Atacama, and that is the ACT telescope. I think you're the only, maybe the only person who's actually worked on both, and also simultaneously worked on both as well. And he's now working at the Simons Observatory, and he is a co-chair with ADI of the Technical Council for CBS4. So I'll stop. Oh, I should say that his proudest accomplishment, I'm told, the thing that he has built, is a real wood oven at his house. So we'll go there someday. Anyway, Jeff today is going to talk about advancing cosmology, ACTPol, and onward to CBS4.
Thanks, Ron. Yeah, I actually learned the skills to build the pizza oven by putting together the mirror for the South Pole telescope. It's the same type of tiling thing, but it's amazing what you can bring home with you. Okay, so today I want to talk to you about advancing cosmology, ACTPol, and onwards towards CBS4. And really this is a story about the great science that we're doing and that we want to carry to its logic as far as we can. And I think we all know that the universe began, we now understand the universe began maybe 10 to the minus 34 seconds into its current expansionary phase with something that could have been inflation, but where quantum fluctuations were stretched and amplified by the expanding universe and laid down to become the initial perturbations from which all of our structures grow. And just the fact that that happened at such an immensely short time after the beginning of the universe, at a time that's maybe a billionth the time it takes a photon to cross a proton, and an energy scale of maybe 10 to 30, a trillion times higher than is accessible with a Large Hadron Collider, makes it a really exciting thing to learn about in terms of physics, right? I mean, when I was in high school and starting to read popular press books, people talked about how we understood things well back to the first second, and now we actually have constraints that push back to a tiny, tiny fraction of a second. So that's really exciting. The other thing is that, as the universe expands and cools, you go through all sorts of, energy scales, which means that light relic particles that can fall out of thermal equilibrium can be created, and those too can leave imprints that you can see in the cosmic microwave background. So the CMB is exciting because you can sort of look back in time towards the very beginning. At the same time, as that radiation propagates towards you, it gets subtly distorted by the intervening matter and things in the universe to pick up additional imprints that can help you go after things like dark energy, dark matter, and the sum of the neutrino mass. So it's just a really exciting area to work in. But of course, the way we're advancing it is experimentally. This is a data-driven field, and that data has to come from somewhere. And we're building this succession of experiments that become ever more precise. And I want to tell you about ACTPol and advanced ACTPol, which are experiments that are both just finishing up and also in the field right now, but also how that technology is carrying forward to do even more ambitious things. And the thing that we have on the horizon is doing a very broad community-wide project called CMBS4. And so I want to tell you both about how we're going to do it and why you should care, why this is a really exciting direction for research. So the thing that's been, and just to warn you, I just want to remind everyone that three of the things that we measure in the CMB are the spectrum of temperature fluctuations, and then the two for polarization, the so-called E mode and D mode. And the E mode is the curl-free part, which is sourced by density perturbations, and then the B mode is created by gravitational lensing and also from tensor perturbations early in the universe. Now the reason I'm showing you, I'll come back to this later, but the thing I just want to point out is that there's a lot of dynamic range there, right? There's order of magnitude smaller and smaller signals. And if you think back to, when I started this field in grad school, the temperature was just detected and the polarization hadn't been detected. And this is a really ambitious goal to sort of move the field forward and get there. And we made a ton of progress on it. So I want to start by just reminding you how we're doing that. And I wrote down this Moore's law, which is just experiments I've worked on and the number of pixels that are fielded on there. And if you look here, this starts at 10 to the 0, which is 1. And if you look really carefully, it goes up by something like an order of magnitude every 5 years, which is a staggering rate of growth. But Moore's laws fundamentally are mathematical curiosities about a multiplicative growth in linear time. And we have the same thing for obviously Moore's law comes from semiconductor physics and computers. But if you actually think about that, that's actually a fairly boring statement too. What's exciting is that that technological progress brings about radical change in our lives, right? I mean, if we think back to the 2000s or late 90s, artificial intelligence was paperclip helper interfering with your typing and saying things like, I see you're trying to type the word and, how can I help with that? There are only 5 steps to typing and, you think, wait, there's 3 letters. And it wasn't quite that bad, but it felt that way to me. And then you fast forward and you ask that, you back out of your car, out of your driveway in Ann Arbor, and you say, oh, I've got to figure out directions to the Sophie Hotel in Chicago I've never been to. So you ask your car, you don't check it, and it gets you there, right? And that's what 10 years or more, 20 years or Moore's law gets you. And the same thing happens in the CMB, but I wanted to take a time to appreciate how that looks, and hopefully you'll have the same emotional response to it when you look at it too. So as John mentioned, I started out not only in New Jersey, but in this handmade stage, which is before stage 1, stage 2, and stage 3, and even stage 4, working on these early experiments that have 1 pixel. This is what they look like. We all talk about how we're experimental cosmologists, and you think, well, there's only one cosmos, how can you experiment with it? And the point is that we actually use the tools of experimental physics to develop new instruments, bring them to the field, and make the best measurements. Now, this is actually what a state-of-the-art instrument looked like in 2000. You can see a fan, if you look really carefully up there, that little white thing. It was bought from Dwayne Reed or something for like $1. And that was a crucial piece because it kept it from overheating so we could run longer and get better data. This is what the teams looked like back then. And in fact, it was basically one professor who's Suzanne, one grad student, Matt Hedman, who was also a KICP fellow, just to be a little more Chicago-centric to follow on John's lead. you know, basically they built that, and then I was an interloper who came in the first year of grad school to help with some of the observations. So these teams started out really small, but it had that fire where you could just go, think of an idea, figure out how to build something and make it happen. I think that's a really important piece of what our field looks like. I would show you the data from it, but it's actually boring. It's a single likelihood curve that shows a limit that was at the time the best limit. But you know, if you think back to the power spectrum, we were ambitiously trying to measure the E modes, and we wanted to get there. Now, if you go to my thesis project, this is what some of the receivers looked like. They were this big. They were hand assembled. It took someone a month to make them. It's barbaric by modern standards. The sensitivity wasn't even that good. But the team got bigger, and we were, with the 16 receivers, we were able to do quite a bit more. And the one thing, it's really dark, I'm really sorry to say that, but there's one person there I just want to acknowledge, who was Bruce, who was the other co-PI of that project, and you know, I learned so much by working with him. It was really fun. So I just wanted to kind of reminisce over a picture as much as why I did that one. But if you look at what we achieved, the red points show our measurement of E modes, which wasn't the first. Daisy got there first, but the point is that by making these sort of improved measurements and improved instruments, we were able to make this progress and make an E mode actually show up as visible for the first time. So we talked about stage 4. What is stage 1? Well, really the thing that's transformative, that changed what our field can do, is the move from doing these hand-assembled giant radiometers based on you know, the technology we had at hand, to these custom-made lithographically etched monolithic TES arrays. And this is one of the arrays up there. As a triangle, has about 160 detectors. You put those together, you get about 960 detectors in the array. And with that, we ushered in this new era for what you could do with the temperature. This is what the team looked like. This is a younger me and a slightly younger John, a little bit pixelated. But this is where we were building the South Pole telescope. And the results that came out of that, I mean, as you know, are just staggering, where we have these beautiful images of large swaths of the sky in temperature, where you can see things like the first one. Cluster detections, that's not actually the first one, it's just an example, where you can actually resolve individual clusters. But also one of the things that I'm most excited about from that era, which is measuring the damping tail so you can actually constrain inflationary physics in the form of the scalar spectral index. And so, you know, the temperature went from being sort of measured to being incredibly well measured, and measuring, I think, 9 or 10 peaks, depending on how you count, because of this advance in technology. Now, carrying forward our Moore's law, you get to the era of arrays that are measuring temperature and polarization. And kind of the key advance is that we figured out how to manipulate the fields through superconducting microstrip and actually separate polarization and manipulate bands on chip. And with these, this is the same detector that went for ACTPol, but I'm showing you ACTPol, which is what I probably spent more time working on after I left here. We were able to make, God, that's really pixelated. Looks good down here. That's funny. Anyway, so the teams got bigger, but the results got even more exciting. And so now, instead of just measuring temperature, we also have polarization, which I'm showing as Q and U, and then really nice maps of the E mode. And you see that, you know, the measurements of the polarization, which were looking kind of ratty, are now starting to look very crisp and well-defined. And so this, you know, Moore's law is giving us, you know, not only more detectors, but the science is just getting more and more beautiful, and we're measuring things we couldn't see before. And along that line, I think one of the most exciting things from this this stage is the fact that B modes, which are the long sought after goal of the field, have been measured, albeit not at the precision that we'd ultimately like. We really want to do these tighter so we can really get the science out of there. So then.
Is that curve with a specific value of R?
Oh, R is 0. Yeah, the foregrounds have been subtracted. Yeah, we'll come back to that too. This is the raw part about Moore's law being important. I'll come back to the details of what science you get out and go into that a little more carefully later. I just want to get across the progression and how meaningful it is. So then, the next stage is that how do you make progress? We've developed arrays that measure temperature and polarization, and now we want to get to more sensitivity. And the key is, how do you do it? Well, our detectors are background limited. That's why I'm showing this Moore's law as the fielded number of detectors, because that's a proxy for mapping speed and experimental sensitivity. And so the only way forward is to start building more and more arrays. And so advanced ACTPol went to having 3 arrays, but also upgraded to maximize the sensitivity. We learned some things in the first generation. And where we are right now is that with data up till last year, this is an example of a polarization map which covers about 20,000 square degrees, which is about half the sky, of which 15,000 square degrees are deeper than Planck by something like a factor of 1.5, and 18,000 square degrees are about a factor of 2 or more deeper than Planck. And so, we'll compare these later on, we'll spend a little time going through it, but the point is that, again, we're at this point where the ground, because we've been making this progress and pushing the technology and the measurements forward, we're at the point where we should be able to make better constraints, or will be able to make better constraints on cosmology than Planck from the ground. And so we're going to move into the era where ground-based cosmology is going to be outdoing space, and that's something that I'm just really, really, really excited about. Also, because it's on the ground, we can have 5 times Planck's resolution, which allows you to do things like cluster astrophysics and other things really nicely. And so this one is not data that's ready to be published. We're working on it. It'll probably take us another year or so. But what I want to get across is that we can actually observe large amounts of the sky with high precision from the ground. And that gets us to what the thing is that we want to do next, which is the future, where we want to scale up even more and go from sort of this handful of arrays. SPT3G has 9, is that right? 10 arrays, and go up quite a bit farther. And so with the Science Observatory, which is one of the projects I'm spending a lot of time working on, we're going to go to about 50. And then the goal is to get to CMBS4 and go to hundreds of arrays and really get the science that we can out of the CMB. So hopefully I've convinced you that this path of making better and better instruments has been fruitful. Now the question is, what's next, and where do we really stand with cosmological constraints? So this is a standard cosmological model. I won't belabor it. I think everyone here is pretty much an expert. But the point is there are just a ton of things that are really excited that we can do with these data. Because if you look at it, the reason this is here is that we have measurements that include Big Bang nucleosynthesis, the CMB, optical measurements at a range of redshifts, and all of them can be fit with one model that has a few parameters that are free. But the thing that's exciting about that is that the free parameters require physics that is not in the standard model, and that points to some of the biggest, most exciting mysteries that we'll have for the coming century. So this involves things like, how did the primordial perturbations get generated? Is inflation right? And measurements we can make of what patterns we see in the CMB will constrain those, and thereby constrain the energy scale of inflation. We could discover evidence for gut scale physics, or we could even discover that there is some new symmetry in string theory that we need to have. And that is really neat, because as someone who came into grad school thinking that the ultra high energy universe grand unification is really exciting, this is a place where we can actually make measurements and perhaps even find evidence for the quantization of gravity. Then, of course, other things that are in there are light relativistic species. So as the universe expands and particles that are hard to find on accelerators fall out of thermal equilibrium, you could see that imprint of that in the CMB and learn something new about physics that way. And then, of course, in the more recent universe, you have dark energy, dark matter that are dominating, which are about 95% of the universe, and that we don't actually know enough about. We'd love to learn more. And then finally, there's other things like the sum of the neutrino mass that cosmology can help with. That is just a kind of workhorse physics question of what is the sum of the 3 generations of masses of the 3 generations. That if we make it, it's just a beautiful physics measurement. And so this is really why I care about the CMB, and I think why many of us care about the CMB, and why I'm excited that we can make progress. Now, there's 2 ways that the CMB can be used. The first one is that we can just look at the anisotropy. This is an old WMAP map of the whole sky. The point is it has temperature and polarization, and we need to measure both of them. And if you do, those signals can carry the imprint of inflationary parameters, light relics, and many other things. But then, as that signal propagates to us over there through the universe, it traverses all the large-scale structure that's formed since it was emitted 380,000 years after the Big Bang. And that gives you sensitivity to dark energy and dark matter, neutrinos, and a bunch of astrophysics through these secondary parameters. So basically, we want to make measurements of all of these things, and I want to spend just a few slides talking about where we stand and what we're going to get out of these by going forward. So this is the CMB power spectra as they're currently measured. And what you see is that the temperature is measured unbelievably beautifully. There's very little more information we can get out of the temperature's power spectrum. It's at the end of what we can achieve. With the polarization, you can see that the measurements are nice, but you can see that there's still, the error bars are bigger, fractionally than the temperature, and that's one way to understand that we're not at the sample variance limit, that we can actually do quite a bit better. There's cosmology to get out of that. And then finally, the B modes, we've measured them, but the measurements are still quite noisy, so there's a lot of room for improvement. So what do you get out of that? Well, the sort of regions of these power spectra that I want to point you to are the damping tail, which is the high L part. So I should tell you this is multiple moment, so it's measured in L, which is related to the angular scale, so small scales are over there. The damping tail is the CMB at small angular scale, where it's been damped out by being in the horizon. And the neat thing about that is that range of angular scales gives you sensitivity to n effective, which is the number of light relativistic degrees of freedom. So in the simplest case of 3 neutrinos, that would be just over 3. And then NS, which is an inflationary parameter. The two inflationary parameters I want to make sure you guys are thinking of are NS, which is the scalar spectral index, which tells you the tilt of the power spectrum. So since inflation ends, you expect that it won't be exactly constant, because there has to be some change in how inflation is happening that will give you a slight tilt to it. So that's what that is. And so by measuring the high L to higher precision, we can improve those measurements. Then there's the sort of middle range, which I should have had I wonder if I have a pointer. Anyway, if you look at sort of intermediate scales, so sort of right in this zone, gravitational lensing of large-scale structure modifies both the temperature and the E-mode polarization. It's actually responsible entirely for creating this sort of rise in the B-modes that looks suspiciously like the E-modes. Why that's interesting is that is sensitive to the growth of structure, and growth of structure can be influenced by the sum of the neutrinos and other things. So if you change the neutrino mass, you'll change the amount of lensing, and so that is a place where we can have a nice constraint there. And then finally down here, this is the B modes from primordial gravitational waves, which I've just cartoonishly drawn on as a bump, but there's a bump that sort of happens down here, peaking around L of 80. And it is really one of the holy grails of the CMB research, which is why I borrowed the Monty Python's image. But the thing that's really cool is that this tells you, is directly related to tensor perturbations early in the universe, which tell you about the primordial gravitational waves. So these are the constraints that came out of Planck and Bicep for the tensor to scalar ratio, which is the amplitude of the primordial gravitational waves, and the scalar spectral index. And I used the CMBS4 plot of this because I think it's really cool, because it shows that there's sort of two primary models that are families of models that are consistent with the value of NS that we're getting and most natural. And those are the monomial models, which are like 5 to the n. So let's see if I have this. Yeah, so basically these models are like phi squared, and if we went up here, you'd have phi cubed and phi to the 4, which are the first models that I learned about when I was in grad school for inflation. And what I'm really excited about is that, originally, SPT put constraints on NS and also put a limit on R of 0.1 from just the temperature. And so we've been able to rule out more and more models over the last, decade. And so we're getting to a point where we can actually rule out models that people have considered for a very long time in inflation and just say those didn't happen, and constrain what people should work on. And I find that really compelling. But what's really exciting is that we're getting to the point where we can now also put constraints on R from polarization. And Bicep is currently, Bicep CAC 14 is currently contributing to this and leading it to about 0.7. But if you look at this plot, you'll realize that there's a lot more room to go. We'd love to be able to find out what the inflationary theory is. And I think the thing that I'm most excited about is that we could potentially make a measurement of R. and find primordial gravitational waves, which will tell us something fundamental about the universe. This plot shows what would happen if, R was undetectably small for CMBS4, and what limit we put. And the point of this is that we'll be able to rule out all of these monomial models, so anything that's phi to the n, and that's one of the two theories that's most promising. And the other one is these plateau models, where there's this characteristic scale over which the potential varies. And CMBS4 will have the power to actually limit that to for n less than the mass, the Planck mass. And what's neat about that is that if it were larger and we detected it, which there's many models which could be up here, then that would tell us something about a symmetry that it has to exist for these high energy theories. And at the same time, if we don't see it, then we actually start ruling out some of the symmetries and start helping with understanding how the physics works at very, very high energy. But the thing that I'm most excited about is that we could, in 10 years or 5 years, get to the point where this data is so good that we actually have a measurement of primordial gravitational waves, and we learn something that is real evidence for the quantization of gravity. So anyway, I think that's just going from where we are now to this level will be a really huge achievement. Of course, that's not the only thing you can do with improved CMB measurements. Another thing you can do is you can constrain through the damping tail the number of light relics. And of course, we all know that there are 3 neutrinos. Those are light relics that definitely exist. But the thing is that, and we've already made measurements from Planck that actually rule out another neutrino decoupling at around the same freeze-out temperature. Right, so this is freeze-out temperature, this is the change in ineffective from 3. And so we've already ruled out that we have another neutrino that decoupled at the same, freeze-out temperature as the 3 that we know about and love. But the point is that you can actually introduce new things into your theory that will that decouple at higher energy, that will lead to fractional contributions because of just the number of degrees of freedom that are around at the time, right? Because we've normalized this to neutrino decoupling when we do that calculation. And what CMBS4 will be able to do, it'll be able to take these limits right now that rule out anything up to a little bit above the neutrino decoupling temperature, all the way up to the QCD phase transition, and just rule out any particle that is light that decouples below the QCD phase transition. So that's, it's just neat that we can actually make that progress and learn about these sort of particles that would be hard to measure in accelerators. Now, of course, if we look at this carefully, we can also make a few order of magnitude jump in the particles that have spin. Obviously, the spin of the particles affects the number of degrees of freedom and leads to different predictions. And then if you believe that these things have to have multiple generations, you can put even more constraints on it. But these, I think, are 2 of the main reasons that we wanted to do CMBS for. But the other thing is that you can also improve things like the primordial helium abundance, improve the Hubble constant, search for things like dark matter interactions or ultralight axions, and many, many more things. So this is also just, I think one of my the things I'm most excited about. So for that's sort of 2 of the things you can get out of the spectra. But then for large-scale structure, there's 2 main ways that the CMB can learn about things. One is through gravitational lensing, where the CMB gets distorted on arc-minute scales with degree scale correlations, which takes the temperature and polarization and makes different temperature and polarization. And then, of course, there's SZ clusters where photons propagate through an SZ cluster, a cluster which is a dark matter halo with a small number of galaxies in it as a fraction of its mass, but much more gas. And the gas is so hot from falling to the potential well that the photons interact with the electrons through inverse Compton scattering, and it changes the spectrum and leaves these visible signatures in the CMB, so we can get catalogs of lots and lots of clusters that we can then use in cross-correlation with gravitational lensing to learn to measure their masses and then do dark energy and things like that. So this is unlensed CMB, and this is lensed CMB. And I think we've all stared at things like this and realized how unbelievably small the distortions are from the signal. And I think if you've wondered how we can actually take that and make that into a precision measurement, you can either read the literature, or what I realized is that me, Joe Dunkley, and Renee Holzlak worked together to put together the CMB summer school so that we could teach the students and provide code that people could understand that's really digestible, so you can actually learn how to do this. And in fact, if you want to go make these maps, I invite you to go to this website, download the code, and then you'll be able to do it. And the thing that's fun about this is that CMB lensing seems like a little bit of a high hurdle, like it would be a hard thing for you to do. And I worked with the ACT lensing team, Alex Van Agelen and Matt Yelly, I pronounced his name wrong. And they at first said there's no way we can possibly make a code that will just work standalone for students to do this. And after talking with them a bit, I convinced them that they could do it in 3 lines. And they did. So basically, is you take the same code that we use to generate these CMB maps, which is actually also in there. You generate a deflection, a lensing map from that, and then you use a standalone routine to apply these distortions using only like a NumPy library to do it. And so you can actually get the maps that are here, almost trivially, which is kind of fun. I mean, I don't know that I would use them for science, but in terms of understanding, I think they're really good. The other thing is I had them make a lensing estimator, which will allow you to take this and reconstruct the lensing potential. So if you want to play with it, I invite you to do it. After they did that, they said that they were mad at me because after people saw this code, they would realize how easy their job was. And of course, that turns out not to be exactly true because you have to also deal with all the biases. So they actually have a really, really hard job. But it was very gratifying to both work with everyone to sort of teach this class and get the science across. So with those techniques, this is one of a nice representative map of the state of the art, where we actually now have these lensing maps from Planck that cover large portions of sky, and similar ones from ACT and SPT that are on smaller patches and higher resolution. And if you actually look, we have these beautiful constraints of the lensing over a huge range of multiples, all the way from 2,000 down to low L. And so this, I remember when I first heard about this field, I thought, wow, doing lensing, that'll require almost impossible measurements, but due to the progress that we've made over the last few decades, we've made great progress on making these, and now this is actually reality. In terms of where we want to go from now, you can look at constraints that come out of lensing for the sum of neutrino masses, and how those compare with the electron neutrino constraints from the ground, and you see that they're just on different axes, so they're not exactly in competition. They're very complementary. But with current cosmological limits, we have an upper limit on the sum of the neutrino masses of about 0.112. But what we'd love to do is actually make the measurement precise enough to actually detect a non-zero mass. And the goal for CMBS4 is to actually shrink the limit so that we can have a significant detection. And the projections are such that, like, if we have a minimal normal hierarchy, we should be able to tell the difference between a normal and an inverted hierarchy for the different models, which would be great. And then I just think it's awesome to be able to take cosmological measurements and put constraints on just particles. I think that's a really, really fun thing that we get to do. Of course, that's not it. We also have the primordial power spectrum, where there are other ways we can constrain inflation. So I'm not going to go into a lot of detail on this, but you can actually reconstruct the power spectrum, take your CMB measurements and reconstruct the power spectrum initially for that came out of inflation, and that gives you another handle. You wouldn't predict anything. If you basically see something here, you can directly learn something about new inflationary models. The other idea is you can search for non-Gaussianity. And then, of course, there's the Hubble constant, where advanced SAC will tighten the constraints on the Hubble constant. There's this anomaly between Planck and the supernova measurements. And it would be great to be able to weigh in and find out whether Planck is right and move that to higher precision, or learn about whether there's more, really is evidence of new physics or not. And then, of course, there's axions and nucleosynthesis. So there's just a ton we can do. The thing I think why I like these experiments, yeah.
So for the H-naught, is that projected sometime in the future?
Absolutely, yeah. So let's see, this is the SO projection. let's see, ACT will be able to do just slightly better than Planck. And so this is a projected measurement for probably 7 years from now.
And you put it there just to have it in the middle?
Yeah. I mean, I'm an experimentalist, I'm agnostic, so I didn't want to favor.
Well, liver reach is 1 over the square root of 2, so you have it in the right place.
Yeah. No, I mean, God, if I would be giving my talk entirely about this if that was a measurement. Yeah, but thanks for clarifying. Yeah, these are projections. So, what's the path forward? We need better measurements. So what we'd love to do is live in a world where we have these measurements that are these gray bands that you can barely discern from the theoretical curves. And then we'll just get these unbelievable precise measurements. We'll learn about primary gravitational waves. We'll do all of this science. But to do that, we need dynamic range. We have to be able to cover angular scales that go from maybe 5 or 10 degrees down to 0.05 degrees. And we need sensitivity and control over systematics, right? We want to go from these signals up here that are sort of 100 microkelvin down to nanokelvin type signals. So this is a big experimental challenge, which is why we're not done with it, but why I'm excited we've made so much progress. And of course, in terms of systematics, one of the most important things if you're hunting the Holy Grail is not to get taunted a second time. And so dust foregrounds, synchrotron foregrounds, we've got to be very, very, very careful of those. And there's a great way to do it, which is that it turns out that the spectrum of dust gets brighter at high frequencies. The spectrum of synchrotron gets brighter at low frequencies, but B modes in these units are roughly flat. And so if you make measurements at a lot of different frequency a lot of different frequencies, you can then do component separation and figure out what's synchrotron, what's dust, and then get a clean map of the CMD. And this came from a detector proposal, so you'll notice that these are things that we've made, these are things that we're working on. So now, of course, to actually achieve the sensitivity, you need to really max out your, get the detector number up because detectors are background limited. And so I'm going to tell you about 3 experiments that I'm working on. One is ACTPol, advanced ACTPol. This exists and is in the field right now. And the reason I want to tell you about this is because the technology we've developed for this will be totally useful in getting beyond this. The next experiment is Simon's Observatory, which I've spent a lot of time thinking about recently, which is going to start going to the field in 2020. I'm on sabbatical right now, so I've spent all my time in lab hiding out, trying to figure out how to actually make a lot of the things that go into this. But then thinking farther, to really get the measurements that we want, we need to get to something even bolder and bigger, which is CMBS4, which will unite the efforts of Chile and the South Pole, and the goal there is to try to get this to the field in about 2027. So I'm really thinking about showing you this to tell you where we stand and what technologies exist and how we're actually making these things happen, with the idea of telling you about this experiment to tell you about how we're scaling them up. And then with S4, one option in the reference design is basically to make bigger versions of this in Chile to do the high resolution science, and then for the low resolution science to do smaller refracting telescopes that won't exactly be like what is in SO but are related to it. So I want to tell you, kind of about the technology, but also about the instruments and how they work. So this is the ACTPol instrument, and it's comprised of 3 cameras on a 6-meter telescope in Chile. And so the light comes in from the telescope, gets focused down. And those cameras are split so that we have bands both for dust channels up to 220 gigahertz, for these middle channels, 90 and 150, and then this low frequency channel for synchrotron that we're going to put in the field soon. And the goal for the proposal was to cover something like half the sky, and this is an outline I made for the proposal. I'll come back to what the data look like in a second. Now just as a basic, one of the things to understand, and this is very old, and I think I actually borrowed this from an SPT talk, is how our detectors work. And what they are is they're bolometers, so light just comes in, gets absorbed, heats up, and then you couple it out with a thermometer which measures how much temperature rose, and then you can measure your signal in the sky that way. One of the kind of my favorite analogies is if you go outside on a very sunny day and close your eyes, you can actually just feel which way the sun goes, and that's really what our detectors do. Of course, you have to pull the light, the heat out of them, otherwise they just keep heating up, so you have a weak link to a thermal bath. There's only 2 sources of noise in this system. One is the incoming light, the fluctuations in it, but also phonons that come over this weak link can heat you up and cause other fluctuations. So really the way we deal with this is that we cool these down to about 100 millikelvin. We operate the bolometers at about 150 millikelvin, the bath at about 100, and that minimizes our noise, but it also means that these detectors are individually background limited, which is why we have to build so many of them. And that's really one of the things that motivated our move to these multi-crook polarimeters, where we figured out how to take light down a very broadband feed horn, couple it onto a special thing called an orthomode transducer, which is microwave speed for a polarization splitter, and then do this over an octave of bandwidth, so that two CMB bands go down each path and get separated by a filter before they're merged together in a way that preserves the nice polarization properties of the waveguide, and then detected in the bolometer. So this allows you to get about 80% more mapping speed per detector array, which is one of the advances that we've used to kind of keep Moore's law going. The other thing we've done is we've figured out how to make these feed horns unbelievably small while keeping their efficiency high. And so since designing these things, we've deployed, I think, a total of 4 multi-crook detector arrays on ACT. This is the first one. You see that it's relatively large with about 256 pixels. We figured out how to get the mapping speed up by almost a factor of 2 for advanced ACTPol, where you see these just many, many more holes, which is good because those are each individual multi-crook detectors. And then we've also deployed them in multiple frequencies. So this is really one of the key technologies that we've developed for this program. Of course, I was really excited when I came up with this idea to make these broadband when I started as a professor, but the first thing that I realized, or right after that damped my hopes, is that you can't actually use multi-crook detectors unless you have optics that are also broadband. And but that's a solvable problem. You just need a really good anti-reflection coating. So if you look at our design, to make these large format detectors coupled to our telescope, turns out you need lenses, and those lenses have to be made out of material like silicon that's index of about 3. You need the high index because higher index materials bend things better. You can't make it out of like plastic. And so that's unfortunate because that makes our life harder. This is a bare silicon lens. It reflects 30% of the incoming light. If you use all 3 of the lenses that we need in our system, you would find you get about 10% of the light through. So this is a problem you have to solve really well. And the thing we turned to is actually an old idea that has been used in plastic millimeter wave lenses since maybe the 40s. I think there's a paper I found from like 1947 that actually describes this type of idea of making subwavelength features. Now, of course, I also wanted to get a grant, so I called it metamaterial, which is probably just straight up pandering. But it was successful, so I was happy with that. But what we do is that we just cut. This is about 1 square wavelength. We just cut features with a silicon dicing saw in this way, and then that way, and then do it again for a second layer. It's rotationally symmetric, so it preserves polarization. It just looks like a simple dielectric layer. And the great thing is that we can engineer whatever dielectric we want by just controlling these dimensions. If you work out the numbers, you need to control the width to a few microns, the depth to about 5 to 10, but which is a little bit tough. But the great thing is that silicon fab can actually hold a lot of those tolerances. The hard part, though, is that our lenses are lenses, because lenses are curved. And so we actually had to build our own custom silicon dicing saw that allows us to cut on curved surfaces. This is it when we were early on the development process with one of the ACTPol lenses that wasn't AR coated. This is what that one, I think that exact lens looked like once we were done. And if you zoom in, you can see the evidence of about 2 kilometers of cutting these features in there. And what's amazing is that, for many of the lenses, probably about half of them, we don't break a single post. So you just have, a million posts that you're looking at to make these really beautiful anti-reflection coatings. And of course, if you zoom in farther, you get something like this. This is actually not a model. This is an image made with a confocal microscope, which is a really fancy thing that will allow you to image surfaces like this in 3 dimensions. Now, of course, what I'm most excited about, though, is the performance. The reflection can be controlled to better than 1%, actually a few tenths of a percent over octave bandwidths. And this is kind of a compilation showing for both our 90-150 band, which is in red, and our 150-220 band that we're achieving, close to 0.1% performance over these full bandwidths, which in terms of just a engineering feat for anti-reflection coatings, I'm pretty proud of. but I'm much more excited about the fact that this is enabling for doing the CMB research that we care about. Let's see, I have 15 more minutes about. I just want to make sure I'm paying attention to time. Yeah, good. So this is the Atacama Desert. It's an excellent observing site. On many days, there's not a cloud in the sky. But the problem is that even in deserts, there's water vapor. And that water vapor does things like this. This is a simulation of what the water, what the emission of the water would look like as it passes overhead. And this gives rise to something called 1/f noise, or maybe it's Kolmogorov noise, but if you measure at low frequency or large angular scales, the noise gets worse and worse and worse and worse and worse as you go up. And we'd love to just figure out a way to measure the CMB without dealing with the atmosphere. Now, the great thing is that this is only an intensity. It's not polarized. So if you can introduce some type of modulation in your polarization, you can completely get rid of this. And so the idea is that if you can just make a wave plate and you spin it, then you get an output where you can lock into that signal and completely reject, or highly reject this. And this is an example. It's a proof of principle from an experiment called ABS, where you take this data, which has a 1/f of maybe a few hertz, and you can get it down to millihertz or below. And so this is a neat idea, and we love to do that. You just have to make really nice half-wave plates. Now for ACT, what we realized is that we wanted to put the wave plate warm in front of our receiver. Now to do that, you have to control its emission so it doesn't compromise the noise of your system, because what's the point of having non-background limited detectors or limiting it by a dumb background that you don't want? So what we came up with was we realized we could take this metamaterial work that we've done and cut features that break rotational symmetry. So if you have just a bunch of grooves that are smaller than a wavelength, then this will become a birefringent material. Birefringent is one of those words that I use all the time now that I forgot that I learned in undergrad. That means that the index refraction is different this way versus that way. That's what you need to make a wave plate. Of course, the advantage of this is that you can engineer whatever birefringent, so you can make these things exceedingly thin, right? So you can just dial around the parameters. And then you also have a plan for how you're going to anti-reflection code them, because you can use the exact same techniques we had before. The other thing that's really fun is that you can actually engineer the anti-reflection coding to match the difference of the indices for each individual polarization. This is what the design looks like. This is absolutely the hardest thing I've ever tried to make in my lab, we've ever tried to make in our lab. In fact, it's the hardest thing I've ever tried to make, because it requires cutting completely into one silicon wafer, gluing into another one, and then dicing the outsides of these things. Holding them down with these glues that are microwave velocity that you have to figure out how to clean out using toluene and other chemicals that I've never dealt with. But we managed to make 3 of them, and this is when we first deployed them. And with them, we've actually successfully, measured. We've done about a month worth of observations that that we use to sort of understand how well they work. Now, oops, did I lose? This, I find these to be really exciting, and with these, we should be able to get to very low L with ACTPol. But the thing is that this is only one part of our research program, and so I'm going to tell you about the data that we have that doesn't have the wave plates on them. And the reason for that is that we're analyzing those data while we're trying to analyze our main data, and we don't want to put them on full time and accidentally compromise our ability to get to the small angular scales. So I feel like this is a very forward-looking technology where we've learned a ton that we'll reuse in the future. But let me just tell you about what we're doing with our data that we've been taking that doesn't have them on for a bit. So this is our first 3 years of surveying from season 13, 14, and 15. And the bluer things are, the deeper the observations. So you see that we started out with some sort of deep fields, which are called deep 1, deep 5, deep 6, and so on. And then we have these other wider fields, and sort of moving wider and wider as we've got the instrument working better and better. This is what the data looks like. And this is kind of a fun movie. On this side, you'll see Planck data. On this side, you see ACT data. And what you see is that the noise gets a lot lower as you go to this side, and then the polar, you start seeing point sources, and if you look really carefully, you can even find a few clusters in there. And so in terms of progress, this is a nice movie. Now, of course, you probably could make a similar movie with SPT original data, with ACT original data. But what's really fun about ACTPol is you can make this one with polarization. And it took me a lot of convincing to actually get this one made, because the Sigurd, our map making guru, pointed out that Planck only has noise here, right? You can't actually see the polarization. But in terms of a very clear picture that we're making progress, if you go from having maps where you can't see signals to where you see all this stuff, that's pretty exciting. And on the upper part, you see the Q polarization, which, if you look really carefully, is sort of aligned horizontally and vertically. On the bottom, you see U, which is a crosshatch, so you have the direction, exactly as you'd expect for E modes. So where this gets us with the measurements is that in the very near future, we're going to publish our results, which will give a TE spectra, an EE spectra, and also B spectra, where we're going to tighten our error bars by a factor of 3 or more over what we've already published. So this is an exciting piece of progress, right? I mean, we're just getting there. If you look at what that's going to do for cosmological constraints, if you combine these ACT data with what you get out of Planck, we're going to get within about, we're not going to improve cosmological measurements. Sorry, if you combine ACT with WMAP, what you find is that we're going to get, in some cases, within 10 to 20, 20 to 50% of the Planck measurements. We're actually getting very close to the point where our measurements plus WMAP will actually rival Planck. Of course, we'd like to go farther, but the data that I've showed you so far only go up to season 15, and we already have 3 more years in the can, and we're taking more data. And that data is the advanced ACT survey, which covers the 20,000 square degrees that I was showing you early on. And this is what the coverage map looks like. And so you see that we're really efficiently observing a large part of the sky, but this is what the actual maps show. This is the temperature. To be fair, I'm actually combining Planck with advanced ACT here, so that some of the large-scale features are a little bit, on large scales are probably dominated by Planck here. But if you zoom in, what you see is that we're actually getting to the point where we can see individual galaxies, which is kind of fun. I didn't anticipate that that's what one of the things we would do, but it's fun, and we've actually had to use like IR catalogs to go in and mask and remove these things. And then a ton of other small scale stuff. But where I'm really excited is that we have these E-mode polarization maps that are covering a large fraction of the sky and much deeper than Planck. This is what it looks like from us. I'm going to blow it up a little bit just so you can see. This is sort of the central portion, so you see it's kind of in between here and here. And this is what we get with B-mode polarization. And the reason I'm showing you that, don't take a power spectrum in your head, but it's so pixelated you'll be fine. The reason I'm showing it to you is that we have different depths in our map. So this is deeper than the whole thing. And you see that there's really no difference. So everything you're seeing in here is signal noise, is fairly high signal noise. This is a neat new thing. The other thing is you can look at what you get from Planck, and if you compare ours to theirs, it's actually a little bit, it looks better on my screen. You just see these large swaths where it's just noise dominated, and then when you go to ours, you just see it all in high resolution. What's that?
Is that a noise structure, or is that signal structure?
For Planck, this is their noise.
That's noise structure.
That's noise structure. Now that's the galaxy, that's real, right? And you can see it coming into focus better for us. But
So the stuff is like that because of standing time?
Exactly, that's right. Yeah. But the thing I'm very proud that we actually have maps over a large swath of the sky that when we analyze them should allow us to improve cosmological constraints over Planck, and move that forward. Because it's almost fun to do measurements, but they're not really fun unless you're actually moving the field forward and doing something.
What's the lowest value compared to Planck? You can't.
Oh, low L, no, low L, Planck kills us at low L.
Yeah.
Yeah, there's no question.
So where's the crossover?
Let's see, the crossover we're I'm just going to say of order a few hundred without being exactly explicit about that. I mean, I think by the time you're getting 500, we should be completely winning. In fact, probably, and I think somewhere around 200, but I'm not exactly sure about the crossover. But just, the number of modes we measure is vastly higher, and the signal noise is vastly higher. And that's the part that I'm excited about. Okay, so now going farther, ACT maxed out completely what we can do with that instrument. We filled up the field of view. You can't put more detectors on it and get anywhere. It's the end of life for that, so you need more. And what we're doing with Simons Observatory is we're building a 6-meter telescope that's brand new, that has an unbelievably large field of view. I'll tell you about that in another slide, which will have 30,000 detectors. And then we're going to build 3 small apertures, which are targeting the B modes, which will be about just under half a meter clear aperture with an additional 30,000 detectors. This is a picture, early picture of what the site might look like. We've actually advanced a little bit. We've decided to get rid of this fourth telescope since then. But this is what the large aperture looks like. It has two unbelievably large mirrors. So the novel thing is it has a 6-meter off-axis primary, but also about a 6-meter off-axis secondary. It allows us to couple to these giant several-meter diameter cryostats, which can house up to about 120. I think when fully outfitted, we could get to about 100,000 detectors, which is just a massive piece of progress for what you can get on an instrument. The receiver we're planning is going to have 13 optics tubes, each of which can hold 3 detector arrays, which is basically, each optics tube will be ACT in terms of number of detectors. In the interest of time, I'll show you, this is what our giant cryostat looks like. This is a person. So we're starting to move into the very big science era of the CMB. This is what the optics tubes look like. They're about 1 meter in length. They have 3 silicon lenses, again, like we saw in ACT, with detector arrays back there. If you actually look at what components are going into them, we're using the same anti-reflection coating lenses, the same detector arrays, and then also a few new things that I probably will skip over. For the small apertures, again, we're building it out of the same types of pieces, where these are now much more manageable systems, but they're built from the same pieces. And so what I want to get across is that we've learned enough in building these instruments that we know how to scale up. And what we need to do is just build these things and get them done so that we can actually go through and get the full science potential realized of the CMB. Now, you might think scaling up is a boring task, but it's not. There's so much room to still have innovation and have fun and do the things that feel like small science. One of them is that we built an entirely new silicon dicing system in our lab, and we're going to take the time it took to make one lens down from something like 3 weeks to a couple days. And this, it's funny like what it takes to do that, but what we decided is we just need to have multiple spindles so you could cut different width slits all at the same time and rotate things. And this, in terms of hands-on research, has been really fun because we now just have this computer code that is almost at the point of just making lenses. We put something there, and then you can walk away. We're transitioning from having Joey, my grad student, work on this to just having a technician. We'll just put a lens down, press a button, and then we'll go. We've also started developing laser metamaterials so that we can cut other things like alumina. This is progress that was from December, where we figured out how to turn on this laser and actually cut square structures for the first time. Turns out like lasers are really interesting and fun. They're following their own Moore's law, which is enabling all sorts of new things to happen. And then of course there's other things like developing new components like special NASA sun shader inspired diffraction control to minimize side lobes and all sorts of other things. Now, the one slide before I end, I just want to point out that all these technologies don't just do one thing. So whenever you're a hammer, everything starts looking like a nail. And there are other fun things that you can do. So for instance, we're collaborating with Toltec to develop lenses and feed horns that will go on so that they can image galaxy clusters at high resolution and do X-ray style imaging from the ground just using the SE. With CLASS, we're trying to go after the large angular scales and measure how stars turn on, which is called tau, and we're contributing lenses to that. And then with CCAT, there are fun opportunities to do things like C+ spectrometry, where you can actually look at the universe between redshift of 2 and 10 and look at how stars turn on and trace large-scale structure. And we're working on new ideas for detectors with them. But I'm just going to end with this, which is why we're doing what we're doing, right? Here's stage 2, here's stage 3, here's stage 4. Here's some of the science topics I talked about, including inflation, where we might be able to see evidence for primordial gravitational waves, which we could detect, or if we detect them, that'd be great, or even if we don't, we can rule out some of the most compelling ideal classes of inflationary models, and we can rule out whole classes, which is neat. For light relativistic species, we should be able to detect or rule out all light relativistic particles that decoupled after the QCD phase transition started. And then for neutrino mass, we should be able to make a 3-sigma detection of neutrinos, the sum of neutrino masses. So I think this is an exciting time for CMB cosmology. I feel like we've made a ton of progress for instruments, and I hope that I think I'm very excited about what this future will bring, and I'll just stop there and say thanks.
Questions? Jeff?
Yeah. So, I guess 2 questions about the lens.
Yeah.
Okay. Yeah, I just have 2 questions about the lens thing. So, one, I guess the roundness was sort of challenging, but if you're making metamaterials anyway, why don't you just make the lens part of your metamaterial?
Oh, right, yeah, so you can use like a gradient index lens. So we've thought about that a little bit, and it seems kind of compelling to make the thing you have to manage is that you have to make these things anti-reflection coated lenses and not scatter or do other surprising diffraction things. And with the subwavelength features we're making, we prevent diffraction from happening, right? Because they're subwavelength and it just doesn't happen. I'm a little worried about the variation in the features and the discrete number of features causing diffraction. So I've been worried about that. We haven't gone to doing that. But the other thing is that if you went with gradient index lenses, one of the natural ways you do it was with deep reactive ion etching. But there you're limited to 6-inch easily and 12-inch absolutely, and we need actually larger optics. Now, the other thing you could do though is you could go to just deposited layer. There's a lot of games you can play, but I've been worried about the systematics. That's the short answer.
Relatedly, one cool thing about kind of millimeter waves is you also have metals that work in superconductors.
Yeah.
So you can also have part boundary conditions. Does that do you can actually because you can also make all the part boundary conditions, so then you don't have part boundary index.
So what are you picturing? I should talk to you about this later, maybe.
We're meeting right after.
Let's talk after. Yeah, that sounds great. That'll be fun.
Other questions?
I actually had a couple of questions, but just one to start. So it seems very exciting. Going into the future. One of the worries, for example, in particle physics these days is that with the next round of experiments, there's a chance you won't see anything very exciting. Suppose S4 goes forward. Is there something something analogous to a Higgs that you would be, reasonably confident that you would see in the next round of experiments beyond just bounding things like R and improving CMP data in general?
The high redshift part is just filled with rich astrophysics, and there's just so much you can measure with the high resolution now. So I sort of tilted this a little more physicsy, but the high resolution is guaranteed to get a census of galaxy clusters, especially at high redshift that we've never seen before. We will absolutely measure the sum of the neutrino masses, which is a little bit wonkish, but we're going to get it. And I'm excited about just doing that. For inflation, yeah, we might set a limit, but there's a lot that we'll learn something even if we do set a limit. Now, with something like that, we just cannot know for sure that we will see it or not. But if all we do is set a limit there, I'll be satisfied.
So if part of the excitement is the high redshift astrophysics of those all structures, galaxy clusters, distant galaxies, certainly the lesson from SPT is that's all about follow-up. So what does the follow-up look like for a CNBS4 catalog of those kinds of objects?
The survey that we have will overlap entirely with LSST. And so that's the start. But that's not it, right? And I think that that there's going to be a lot of work to be done there. You're absolutely right about that.
I have a question about your ACT data.
Yeah.
This huge part of the sky and having independent of Planck similar constraints means you'll get another measure of the Hubble constant from how's that going?
These maps we just made in January. We're not there. I know.
That'd be really exciting.
That'd be really exciting. But yeah, this is, I think we have it's this thing where you keep building experiments and you get this backlog of data and it just kills you that you can't focus all your effort on just doing analysis. Because we have to first get the, these results are not published. This is our top priority. We have to get this out, and then we're going to turn our attention fully to that. But we're just not there yet.
Any other questions? Okay, well, before we thank Jeff again, just a reminder for the students to come on up, and the rest of us will go enjoy the reception while they grill Jeff. But let's thank Jeff one more time for a wonderful talk.